let's continue. So I recall you, so it is asymptotic space. Suppose we have a metric space xd. X is some set, d is the metric distance function between two elements. And I define the asymptotic space at infinity. So, in fact, the theory of asymptotic space at a point when you use a microscope is not less interesting, but I simply had the interest in other direction, so I have no interesting examples of this. So let me concentrate on asymptotic space at infinity. So we consider star x. It is, say, non-standard extension of x, which consists of a set star x and a function star d. Now we take epsilon in star r, which are plus, such that epsilon is infinitesimal. Yeah? And consider a space, so I assume that diameter of the space x is infinite. So the distance function is unbounded. The standard distance function is unbounded. Then if you consider the space star x epsilon, it is the same set star x and the function epsilon times star d multiplied by infinitesimal. Then it is also unbounded set. It means that for any non-standard number there exists a pair of elements in star x such a distance is more than this number. Yeah? So it is also unbounded set. And now I define standard of star x epsilon. What is this? We consider, first of all, we fix a point O in x, and here correspondingly we have star O in star x. No, because it's just one point, we can identify it. So this point O is just one point in star x. So we consider first the set, say, y, it is x in star x, such that star d of x O is bounded. So the standard number is bounded if it is less, non-standard number is bounded if it is less than some standard number. Yeah, so bounded means that star d of x O less than some k in R. Yeah, so this means, yes, it is I would say, finite part of our space. Now, here, if you have, say, x and y in y, for y, then I write x equivalent y if star d of xy is infinitesimal. Yeah, if this way, and the equivalence classes related to this equivalence relation, so y over this relation, let me let me denote it z. I don't want to use too many indices. Yeah. Now, if you have x and y, these are x, y, and z. Yeah, so in fact x and y are some sets, equivalence classes relative to this relation of being infinitesimally close. Yes, so to say, being in one monad. What is I define delta between x and y the following way. I choose representative here and representative here, say c in x, eta in y, and I consider star d between psi and eta. Yes? Now, if you take different psi in x and different eta in y, then the result, this distance, will change by infinitesimal number, by definition. Yes, no, I have to use the triangle inequality here. This means that this distance of psi and eta, if you take standard part of this, does not change. So this distance, non-standard distance, will change by infinitesimal. Yes? And so it is standard part. First of all, it is finite. And second, it will not change. So standard part is much coarser. It's sort of coarse graining of non-standard numbers. Yeah? Does not change. So this definition is a correct definition of new distance. No, it is trivial that this is a distance. And so, if you take the space z, set z, and the distance delta, it is a new metric space, which I define x epsilon twiddle. Yeah? So it depends on epsilon. No, implicitly it depends on all of the non-standard model of our universe. So no, and explicitly on epsilon. It is a new space. So x epsilon, it is asymptotic space at infinity. Yes? This asymptotic space. I recollect that last time I showed a couple of examples. No, first example was x equals Rn and this distance, usual distance, and x twiddle, it turns out that it's the same x for any epsilon. Yeah, so the result does not change because for any finite epsilon, not standard epsilon, we have the same space. So by transfer, it remains true for infinitesimal epsilon. If we consider x equals Zn, Z is the set of integers, and this is the same distance as here, so it is n-dimensional lattice. Then, after all these operations, we have x twiddle epsilon is Rn. So, because first, when epsilon is infinitesimal, we get something which is dense in the Rn, and then it turns out that it is super dense. This means that in any for any point of Rn, if you take its monad, the set of points which are infinitesimally close to it, then will be in this monad will be the point epsilon times integer point, super integer vector. So we'll have this. So now let me consider still other examples. X equals here the set 2 to the power n. And the distance is the same distance on the real line. So just absolute value of the difference between the numbers. So consider the set powers of 2. So x is 1, 2, 4, 8. This is our set x. And the distance is the absolute value of the difference. So what is the asymptotic space? First of all, let us take epsilon in star r plus and epsilon is infinitesimally small, and consider the numbers epsilon times 2 to the power n. In this set of such numbers, I must say, let me do it properly. If you consider the original set 2 to the power n, epsilon times 2 to the power n, then we have the following. For any epsilon r plus, there exists n in n such that I would say yes, in n. Let me write here, not in r plus, I take small epsilon, in 0, say 1/4, for example. There exists n in n such that 2n1/2 less or equal than epsilon times 2 to the power n less than 1. Yeah. So we find n such that this holds. So we have this statement, which follows from, say, a Archimedean axiom from anything. So by transfer, for any epsilon in star r, let me write star 0, 1, 4, there exists n in star n such that 1/2 less or equal epsilon times 2 to the power n less than 1. Now here 2 to the power n is also the extension of the usual function 2 to the power n. So n is in star n. So let us take this n. Now let me denote it by n0. 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 Yeah. So we have the following set now. We have epsilon times 2 to the power n0. Now let me denote it a. Yeah. So a between 1/2 and 1. So we found such a. So this means that epsilon times 2 and 0 plus k equals 2 to the power k times a. No, say k is in star n, of course. Star z, so it can be positive and negative. No, in particular, it can be a usual integer z. So we have the following points. A, 2a, 2 to the power MA 2 minus 1 times A 2 minus KA, and so on. So we have these points, no geometrical progression, which is okay. It is for K. Let me K minus M. K in Z. But Z is a part of star Z. So we have this set, and this is the standard part of all these set to the power A when K in star Z. So this if you consider M which are infinite, then a standard part of this is 0. So we have to add here 0. So our set, which we call Z, equals the following. It is 0 union A times 2 to the power K in K integer. Yeah. So all two-sided geometrical progression. So this is and delta of xy equals modulo x minus y, where x and y points of this set. So we found here the asymptotic space, and you see that this asymptotic space is not unique. Unlike previous examples, this asymptotic space depends on some A, or this A is this to the K times A. Now this A, after all, depends on epsilon. Yes, so our construction depends on epsilon. So no wonder that it is the result is non-unique. It depends on some parameter. No, okay. Now let's consider one more example of this sort. X is the set of points 2 to the power 2 to the power k. Yeah. And consider star x equals the set 2 to the power 2 to the power k, such k in star n. This is the set 2 to the power 2 to the power k. It's the set star x. And the distance star d epsilon of xy equals epsilon times model x minus y, as it was before. No, model, because we are standard, so you have to write here standard, non-standard extension of model, but we will skip it because it has all the properties of model. Now the situation is, I would say, steeper, because here we had that at least we had some element of our set which is between 1/2 and 1, and in other respect this element was arbitrary. here we have a difference. So epsilon is infinitesimal. So we have the following situation. We have here two cases. Case one. Each case depends on the non-standard model and on epsilon. There exists non-standard number such that epsilon times 2 to the power 2 to the power n 0 is bounded. And not infinitesimal. Yeah. So let us call it then standard part of epsilon times 2 to the power 2 to the power n 0 equals b. B in R plus. So it is positive and finite standard number. So this is standard part. So what can you say about other terms in this case? So epsilon times 2 to the power 2 to the power n 0 plus 1, for example, equals epsilon times 2 to the power 2 to the power n 0 square equals 2 to the power 2 to the power n 0 times epsilon times 2 to the power 2 to the power n 0, and this is b, equals 2 to the power 2 to the power n 0 times b. Yes? And b is a standard number, but 2 to the power 2 to the power n 0, because n 0 is infinite. Yes? This is infinite number. Yeah? So standard part of epsilon times 2 to the power 2 to the power n 0 plus 1 does not exist. Yeah, because it is infinitely large part, large number. Similarly, standard part of epsilon times 2 to the power 2 to the power n 0 minus 1 also does not exist. This number, it turns out, equals epsilon times 2 to the power 2 to the power n 0 times two to the power minus 2, one moment, 2 to the power n 0 minus 1, yeah? Yes, equals b to the power 2 minus 2 to the power n 0. It is infinitesimal. Yeah? after all these arithmetics. So in this case, so this means that standard part of this is 0 of epsilon times 2 to the power 2 to n 0 minus 1 is just 0. And so in this case, we have that this asymptotic space consists of just 2 points, 0 and b. So all other points which are met in the non-standard first space are either infinitely far away or they are infinitesimally close to 0, so standard part gives 0. So we have just this point. And the second case is that, all right, case 2 is there exists no n0 in star n such that epsilon times 2 to the power n0 is bounded. Not infinitesimal. No, it is easily constructed. Say, we take epsilon equals 2 minus 2 to the power n0 plus 1/2, for example. Yeah. So we halfway between n0 and n0 plus 1. Yes. Then you can see epsilon times 2 to the 2 and 0 equals 2 minus 2 and 0 minus 1/2. Yeah. So this number is infinitesimal, and if you consider epsilon times 2 to the power 2 to the power and 0 plus 1 equals 2 to the power 2 to the power and 0 plus 1, no, plus 1, for example. So no matter, which is infinite. So, because we in this step we go too far, make too fast growing steps. Yeah, so here epsilon is such that the finite numbers, standard finite numbers, are exactly between these two steps. So in this case, our set x star is exactly set contains 1.0. Yeah. So depending on the parameters, we have two cases here. No, it is still not so interesting. And now I wanted to consider more interesting example. Binary tree. So what is binary tree? Binary tree is the following graph. We have a root. Let me denote it by O. This is 1 point. Now you have two other vertices which are connected by edges with O. For each of these vertices, we have two vertices other which are connected with them, and so on. So we have this. This is our space, and the distance is defined by as a distance along the graph. It is the minimal number of steps along the edges to get from one, say, vertex x to other vertex y. For example, we have to go this way, and then this way, for example, in this case. Now, this geometrical picture. No, we can immediately create a isomorphic picture, a symbolic picture, which is more tractable. So every vertex is obtained by finite number of steps starting from O, from the root. Yes, and at each vertex we have to choose go to the left or go to the right. No, of course we can encode this. Go to the left here, right 0, go to the right 1. Here, go to the left is 0, 0, go to the right 0, 1, and so on. So the sequence of these choices is encoded by a sequence of zeros and ones. And so we consider our space X is the set of all sequences A1, AN, such that n is now a real integer number, and AI are equal 0 of 1. Yeah. So for any such finite system, it is finite system, finite sequence, we have some uniquely defined vertex here. Yeah. Now, what is the distance here? And now I wanted to write a formula which maybe is one of the universal formulas in a wide class of situations. If you have A equals, say, A1, AN, B equals B1, BM. It can have different distance. Yeah. So we define distance between A and B equals n minus k plus n minus k. And what is k? K is maximal of J such that AI equals BI for all I less or equal than J. So what is this? We have a sequence of zeros and ones A. We have a sequence B. We write one under other. Yes, and we look where they coincide. Yes, and we look for the first place where they different. At this place they diverge. And whatever is the next, we are going different branches of our graph. Yes, and we'll never meet again. Yeah. So this is the point of divergence, and this is the formula. So, for example, here is x and here is y. Okay, let me write that it is A, and this is B. Yeah, we find the first point where they are divergent. So A, that in this case is 0, 0, 0. And 0, 0, 0, B equals 0, 1. Okay, so they diverge at the second place. Yeah. So the last point where they still not diverge is 1. Yeah. So we have to write this length is 3 minus 1 DAB equals 3 minus 1 plus 2 minus 1 equals 3. Okay, 1, 2, 3. It's correct. And okay, and now this is infinite graph, infinite space. So I wonder what is the asymptotic space of this space. So we have x and d. Here is x and here is d. What is the asymptotic space? So, no, first of all, we have to follow our definition. So, what is star x? X itself is the set of finite sequences. So, star x is the set of hyperfine sequences. Say A of n such that n less or equal than n1 is star n. So it is star x, it is the set of all, first we have the length is the set star n, yes, and the element A is sequence A of n, taking also the values 0 and 1, because this set is finite, so there is no way to no complications from this set. We have complications only from this index. That's it. Star x. And we have star d. Star d of AB equals, say it is n1, n1 minus k plus n1 minus k. What is n1 and k? K equals star maximum of j in
is it k minus n1 or?
Excuse me?
N1 minus k plus
plus m1 minus k. So A is say 1 and 1 0 1 B 1 M1 to 0 1.
So is it n1 minus k plus k minus m1?
No. K is less or equal than n1 and m1.
Oh.
Because at the point of starting from the point they diverge. J in star n such that for all I less than or equal than j, we have AI equals BI. So it is a transfer of the standard definition to this non-standard situation. It's okay. Now let us introduce some infinitesimal number epsilon. Infinitesimal number epsilon, and multiply this distance by epsilon. The same set star x and epsilon times star d. By the way, I have to add here that A of n, or an, how is internal function of n. So what does it mean? Internal, that it is formed by, so this function itself is element of our non-standard universe. So we consider, no, if you return to the basics, you consider the index set for every element of this index set I. We consider some finite sequence, yes, and then we consider this finite sequence as a function of I, yes, and this is non-standard function. No, its equivalence class is non-standard function, yes, and this means the elements of this set are a sequence we choose for all I, or almost all I. We choose some n depending on I, and the value of sequence depending on I, yes, and this all this sequence of these pairs is element is a pair. The first term n depending on I defines as some non-standard number, which can be standard, which can be not, and the second component a, which is either 0 or 1 at any place, will define as the value. No, here it is especially simple because the result will be either almost everywhere 0 or almost everywhere 1. So it will be 0 or 1. So we'll have this construction gives us internal function, and a great thing is that mostly not all functions on the set star n, no, or segments or infinite segment of the set star n with values 0, 1 are internal. There are also external functions. No, for example, a function which is 0 for all finite n and 1 for all infinite n. This sequence is external. Yeah. So we have to distinguish internal and external, and the transfer principle applies only to internal functions. Yeah. Okay. So we consider this space. So in this space we consider the finite part. What is the finite part? The finite part is the part which is at the finite distance from the point O. Point O is just the 0 sequence when we have not 0, just empty set. Yeah, and then we are just in O, because sequence with even one element gives us some other vertex. Yeah, so this means we are wonder what is the finite part. Why the finite part of epsilon star x the set of x1, let's say a1, n, such that epsilon times n is bounded. Yeah, so we should not go too far. No, if we are too close, so if epsilon times n is infinitesimal, it is no harm, because in this case eventually this point, its standard part is at the point O. Yes, so it somehow it's glued together with O. So I don't write here the caveat that it is not infinitesimal. So epsilon times n is bounded. And now let us consider okay. So we have here this distance epsilon times star d. Yes. So we write epsilon star times star d between A and B, where A and B are points in Y. For example, what is this? It is the following. We have to define the first point where they diverge. Yes? So if this first point is the first K, if K is, which is maximum, not star maximum of J AI equals BI for all I less or equal than J, yes? So the point of divergence, if K is such that M minus K plus N minus K epsilon times is infinitesimal. Yes, in this case, these 2 points are infinitesimally small. Then the following, we write that DAB is infinitesimal. Yeah? And now if you fuse all the points which are infinitesimal, infinitesimally close, so take the factor of y by this infinitesimal relation, yes, I will say, and converse. So in other side. So this is when these 2 points are infinitesimally close. And now let me define one space. So now we have to take Z equals Y factored by this identity relation of this infinitesimally close relation. This is our space standard. It is a standard space Z. So what are its elements? So for any Z, say in Z, in R plus, consider Y, let me say A. equals A1 AN such that standard part of epsilon times n equals z. Yeah. So I want so what is my intention now? I want to represent our space sort of as a space of functions with values in R plus, yes, and with argument in R plus and value somewhere. So where is the value? Equals m depending on z. So z is just the monad of the point z. I'm sorry, the set of such binary sequences no. Let me express myself more distinctly. Suppose z in R plus, and consider the set mz equals the set of n and star n such that standard part of epsilon times n equals z. No, this can be a huge set. And consider the set how I do? Okay, psi z equals 0, 1 to the power mz. Yeah, so all the functions with values in 0, 1, yes, defined on this space mz. Now, what we can say? We say that all the non-standard line is a union of sort of monad of the sets mz. Yeah, so any non-standard number, no, at least number, any bounded number around any bounded number z, we have for each such number we can define this set mz. Yeah, so all the set of n such that n epsilon is finite can be stratified into this set mz. So the set of n and epsilon times n is finite equals union, I would say, union without overlapping. Yes, z in R plus these points m such that standard part epsilon m equals z. Yeah. And this point, this set equals union of mz, z in R plus, and here, yes, here is the definition of mz. And for any is the union of mz. And now, if you take any element of our space Y, say A in Y, what it means? It means that A equals A1, AN. The sequence such that epsilon times 9 is finite. It is one thing, yes, and AI in 0, 1. Yes, we have element. We can assign to this element, say phi of A is the following. Let me write phi A of z is the following. If z is less than, okay, it is AK such that K is in MZ. Yeah, so we take out of all this sequence, we take only the part where the argument, the indices are in this set MZ. Yeah, so all this long segment of non-standard integer is somehow divided into non-intersecting sets of MZ, one for each standard real Z. Yeah, and we write in this, take this sequence, so a piece of this. If Z less than epsilon times n. No, okay, then standard. Epsilon times n. Yes? If Z. No, okay, and nothing otherwise. So phi A of Z is defined, phi A of Z is defined for Z in from 0 to standard epsilon times n, not including 0 itself and not including this. Yeah? So it's the function. And what is the image? Where does it take values? It is the piece of sequence, so it takes values in the space of all such sequences. Yeah? So phi A of Z takes values in this set. 0, 1. It is the set of all functions on MZ with the values 0, 1. No, we can equivalent say all subsets of MZ. equals P of MZ. Yeah, no, we identify, we take subset where of elements of MZ where this function is 1, for example. Yes. Okay. At last we, yes, we can make breathe out. What is the distance between two functions? So distance delta of phi a delta between a b equals so a phi a of z z between 0 and alpha, phi b of z z between 0 and say beta, and delta between a b equals alpha minus gamma plus beta minus gamma, where gamma is maximum of sigma phi a of tau equal phi b of tau for all tau less than sigma. So again, we have two functions. One is defined from 0 to alpha, other from 0 to beta. This is gamma, and gamma is the moment of their divergence. Before gamma, they are equal at each point. There, after gamma, they diverge. So here, the domain of these functions is a segment of usually standard line, and the range is such interesting space whose cardinality can be quite high. Yes. Okay. So what we reached after all, we found. Okay, let us consider the space, metric space. Let me call that F. So A phi in F phi of z between 0 and alpha. It is a real number z, and phi of z takes value in I would say 0, 1 to the power mz. Yes, with distance delta between phi and psi is given by the formula which is here. Yeah. So two functions, and f is the space of such function with this distance. I used to propose this space as example of non-trivial metric space in different courses in set theory and in functional analysis. In fact, this is sort of universal construction, and I think these spaces are not fully appreciated, and I will continue next lecture to discuss their properties. But now I want to say that what we did, we constructed some mapping from this x epsilon twiddle. It is asymptotic space of our set of sequences, or of asymptotic space of binary graph, to this space F. We have, and of course, this map is monomorphic, so two different objects are mapped into different two different points of this space are mapped into two different points here. I did not say that this is isometry. It is just embedding of this space. Yeah. So what we found this space of these interesting functions, which is superspace. So it is not subspace, it is superspace. So our space is a piece of that space. Yeah. We can also, I think in every case, in this case also, but I will go to different example, construct smaller space which are subspace of our asymptotic space. Yes, and it is a rare event if you find the isometry, the space which are of such function which is exactly isometric to our space. So what we found here is a sort of approximation of our asymptotic space from above. Yeah. No. Okay. Here we consider a little exotic situation. Yes, but we can consider more elementary examples. Which are also sometimes useful. Consider the space, say, consisted of the pairs, say, A, F, X, such that the function is defined from 0 to A. Yeah? And F0 can be A to R, for example. We can consider even, it is much simpler example. Consider the maps from segment to R. A is arbitrary positive number. And you write D, F, A, okay. A, F, B, G equals A minus C plus B minus C, where C is maximum of T, such F S equal G of S for all S less than T. Yeah. So consider this difference. Yeah. This is also interesting space, but now we ask what sort of functions f of x is. Is it a continuous function, or is it a measurable function, or is it arbitrary function? Yeah. And it turned out it's interesting problem that if we consider continuous f, one example, and other example we consider f which is 0 every body but at finite number of points. Yeah? In both cases we have some interesting metric spaces, But the theorem is that these two metric spaces are not isometric. Yeah. This was found rather recently by Josef Polterovich, who works in the University of Montreal now. We have a full domain of research here, and in fact, little is known. And next time I wanted to talk about much less obvious situation when we can say something about the asymptotic space for another space. Yes, I would say in advance that this space is the hyperbolic plane, or Lobachevsky plane. So for Lobachevsky plane, what is asymptotic space is a really cool thing. Okay, thank you.